Hello students, welcome to the 11th class in nuclear physics. In our last class we had started nuclear reactions and we had looked at conservation laws followed by nuclear reactions. We have looked at the different types of nuclear reactions, and now we move on to the kinematics of nuclear reactions, which will give us an idea about the energy emitted and what are the expressions for the energy which has been absorbed and which has been emitted in a nuclear reactions and then we'll go on to two small topics which are proton induced reactions and alpha induced reactions, which have been specifically mentioned in your syllabus. So moving on to Q value or kinematics and of nuclear reactions. First, let us consider a reaction X plus X giving me Y plus Y, and since we already know what is X is the target nucleus, which is this one. This is capital X. It has been hit by a particle small x, and then this is the product particle, that is Y. It has moved along this direction, and then we have small y, which is the emitted particle, and this is small y. Now students, I forgot to mention why you have to hit X actually, because you see you have to hit it because for a reaction to happen we have a material, and for that material, for that element, X would be an element. So for the nuclear reaction to happen, the nucleus has to be broken so that it breaks and becomes X to Y. So for that, a particle has to enter the nucleus, and the nucleus is surrounded by the electrons, atomic electrons. So what has to be, the particle definitely has to overcome the Coulomb attraction or repulsion of these electrons. If they are negatively charged particles, that X is a negatively charged particle, it will definitely be repelled by the atomic the electrons surrounding the nucleus, and if it is a positive charged particle, it will be attracted, and so its path will be deviated, and there will be no chance of the particle entering the nucleus. For this, usually neutron is a very good particle, incident particle, but then all reactions are not possible with the uncharged neutral neutron. So particles has to, that means since the nucleus is also very small, so you need a very hammer with a very pointed face so that the force per unit area is more, and the nuclear reactions can happen. That's why we always use very small particles, and since it has to have a great momentum, its velocity must be great as its mass is small. So we, as we'll be doing nuclear accelerator in our next unit, not this next unit, this unit itself. So we'll see how these particles are given a very high velocity. So now we are dealing with not the practical but the theoretical part of how they react. So this we know, and we will write capital M and small m. For the nucleus we'll write capital M, and for the particles we'll write for the nucleus we'll write capital N, and for the particles we'll write small n. So we can write that since total energy is conserved, can't we write like this: mx c square plus ex plus mx c square is equal to, see students, by Ex, by the E's we will mean the kinetic energy, and when I say mc square will mean the rest energy. Now students, very important point is that in this treatment of of the kinematics of a nuclear reaction, we have taken the target nucleus to be at rest. So this is at rest and we are hitting it. So since it's rest, it doesn't have a kinetic energy. So see, we don't have a EX term here, because E with the suffix capital X will denote the kinetic energy of the particle of the body X, that is the nucleus X. So we don't have a EX here, we have a E small x. So E small x is the kinetic energy of this particle, this one. And this particle will also have a rest energy mxc square, and it will also have this. But on the other side we have y and small y, capital Y and small y. So since both has got a velocity, both of them have got velocities, they will have kinetic energy as well as rest energy. So we can write this as E capital Y plus m capital Y c square. This is the total energy of the particle, not the particle but the nucleus Y, and plus E of the small y plus m y c square. So you see, the letters here denote the particle or the body or the nucleus that we are dealing with, and E is the kinetic energy and mc square is the rest energy. So this completes, and the equation from the conservation of total energy we have written is like this. And now we introduce Q, the Q value of the reaction, which is equal to E capital Y plus E small y minus E x. Now let this be equation number, okay, let me see, let this be equation 1, x plus x is equal to y plus y, and this one equation number 2, and this equation number 3. So in that case, what we have from 2 and 3, we can obviously write what is Ey plus Ey minus Ex. We can take it like this. This is Ey plus Ey minus Ex. We get that Q value is also equal to capital Mx plus small m small x minus capital M y minus small m y multiplied by, of course, c square. This is what we got from 2 and 3, and this is the Q value of the reaction. So Q value of the reaction, and I will write this as a okay. So if the quantity Q is also called, this is Q value is also called the energy balance, just as in the chemical equations, energy balance. And if Q value is positive, if it is positive, of course it's an exergic nuclear reaction, and if Q is negative, we call this to be an endoergic, then it's a endoergic. Endo Orgic reaction. So this is like this. That means in this type of reaction where the positive Q is positive, energy evolves in the reaction, and here energy is to be supplied to the reaction to take place. So that is the Q value, and there are some other things to find the Q value of this reaction, some calculations. We'll go to the mathematics part now. So for this I'll have to clear the board and okay. So we'll again go to this diagram. We'll draw it again. This was my target nucleus, capital X, and it is in rest. Then this is my incident particle, that is small x. Then I had this target nucleus, it breaks up, it becomes something else, and I have got a nucleus Y, and this is the product particle, which is small y, and this angle was theta. This is the angle of scattering of the product particle. This is the angle of scattering of the product nucleus. So now let's write the equations for conservation of momentum. So by applying conservation of momentum, first let's look at it like this. As we know, momentum of this particle would be how much? Mx Vx, isn't it? So this is in this direction, and after that what we have to do is, since this momentum is directly like this, I have to break up it into two parts, vertical and horizontal components. So I break this into vertical, and so this is in this direction. What do I have? In this direction I have the My and Vy, isn't it? So this is My and Vy, and this is if I write this My Vy, this would be in this direction. It would be how much? It would be My Vy cos of phi, and in this direction it would be My Vy sine of phi. So we have this, and similarly let us look at this one, this small particle that has moved along towards the base. So that is small y, and yeah. So for this particle, its mass is My, so its momentum along this direction would be, along this particular direction would be My Vy, and if I break it, if I resolve it perpendicularly, I will have here, this is the sine component because the angle is on this side, so I have here My Vy sine of theta, because this angle is theta, this one, and along this direction it would be how much? It would be My Vy sine of, sorry, not sine, it would be cos. It would be cos theta. So that means we can write the momentum equation conservation in the vertical and the horizontal direction separately, which we'll do in the part B of today's class.